The universe, as we comprehend it today, is a vast expanse teeming with stars, galaxies, and possibly countless planets. Our most advanced instruments allow us to peer deep into this cosmic ocean, revealing an incredible diversity of celestial objects. Yet despite these profound insights, we are limited by the observable universe. Beyond this visible horizon, there exists a far greater expanse, potentially part of a grander multiverse. Our scientific endeavors have unveiled a plethora of details about the universe we inhabit, but one significant mystery remains unresolved: the existence of life beyond Earth. Despite rigorous searches, we have not yet discovered even the simplest forms of extraterrestrial life, much less intelligent beings. This enigma fuels one of humanity's most profound questions. Are we alone in the universe? The quest for an answer to this question involves several potential scenarios. We could inhabit a universe where intelligent life is common, scattered among the stars and galaxies, or we might be the only intelligent beings in this cosmic expanse. To address this fundamental question, a substantial increase in our knowledge is imperative. The process of achieving this involves distinguishing between what we know to be true, what we assume based on current knowledge, and what remains unknown. Firstly, let's delve into what we know to be true. This encompasses significant achievements in both experimental and observational astronomy, supported by concrete evidence as well as theoretical extrapolations from our best scientific theories. Over the past few decades, we have gained substantial knowledge about the universe's structure and contents. For instance, we now understand the number of stars in the Milky Way and other galaxies, the prevalence of sun-like stars, and the potential for these stars to host rocky, potentially habitable planets. Within our own Milky Way galaxy, there are approximately 400 billion stars. This figure highlights the immense scale of even a single galaxy. The Milky Way, however, is just one galaxy among billions in the observable universe. By studying the metallicity of stars, essentially the proportion of heavy elements compared to hydrogen and helium, we can estimate their likelihood of hosting planets. Stars with higher metallicity are more likely to have rocky planets, which are considered prime candidates for harboring life. Moreover, we categorize stars by their mass and spectral type to determine which ones could potentially host Earth-like planets. These Earth-like planets are defined as those that are rocky, similar in size and mass to Earth, and located within their star's habitable zone, a region where conditions might allow for liquid water, a key ingredient for life as we know it. The knowledge we've gained in the last 30 years is remarkable. We've transitioned from not knowing whether planets existed outside our solar system to confirming the presence of thousands of exoplanets, some of which reside in their star's habitable zone. In addition to these insights, we have estimates about the number of potentially habitable worlds within the observable universe. These estimates are based on our understanding of star formation, galaxy evolution, and theoretical predictions about galaxies that are difficult to study directly. For instance, we know that the observable universe contains approximately 2.2 sextillion stars, a number so vast it is challenging to comprehend fully. Among these stars, different types prevail, including sun-like stars, G-type, cooler and less massive K-type stars, and the abundant red dwarf stars, M-type, which make up the majority of stars in our galaxy. Stars with sufficient metallicity, about 98 of known planets orbit stars with this trait, are likely candidates for hosting planets. Even with these criteria in place, the sheer number of potential habitable planets is staggering. Estimates suggest there could be around 10-19 such planets within the observable universe. This number, however, assumes that we had incredibly advanced technology to detect and study these worlds. To advance our understanding further, scientists often rely on assumptions due to the lack of direct evidence beyond our solar system. One key assumption is that life originated through natural processes from non-life. Given the right conditions and chemical ingredients. This assumption, while widely accepted among scientists, is not without controversy. It posits that life could potentially arise on any planet with similar conditions to Earth or even different but conducive environments. Another assumption is that the fundamental laws of physics are universal, applying equally throughout the cosmos. This includes the processes that lead to star and planet formation, the chemical reactions that could give rise to life, and the evolutionary mechanisms that drive biological diversity. We also assume that life, at its core, involves entities capable of extracting energy from their environment, utilizing that energy for metabolic processes, and reproducing or producing related offspring. Cosmologically, we assume that the unobservable parts of the universe follow the same fundamental principles as the observable parts. This includes the belief that the processes leading to the Big Bang, specifically cosmic inflation, occurred on a much grander scale than our observable universe. This assumption suggests that there are regions of the universe far beyond our observational reach, filled with galaxies, stars, and potentially life similar to our own observable universe. The idea of a multiverse, or an enormous set of disconnected universes, stems from these assumptions. Each of these universes could harbor its own galaxies, stars, and possibly life forms. While we can only observe a small fraction of the universe, the portion within our light cone since the Big Bang, the theoretical framework supports the existence of a vast, unobservable expanse beyond. Despite these assumptions, many questions remain unanswered. For instance, we do not yet understand the exact mechanisms by which life originated from non-life on Earth. Theories such as peptide or coevolution suggest that amino acids and nucleic acids could have spontaneously formed in the presence of water and natural energy sources, leading to the first living organisms. However, this remains speculative without concrete evidence. Furthermore, we do not know how frequently life, once it emerges, can endure for long periods or evolve into complex, differentiated forms. The history of life on Earth provides some clues, but it is just one example. On Earth, life emerged relatively early, no later than 3.8 billion years ago, and has persisted, evolving into a wide array of complex organisms, including intelligent beings like humans. If these processes are common, then intelligent life could be widespread. If they are rare, we might indeed be alone. The possibility of discovering extraterrestrial life, whether simple or complex, intelligent or microbial, is a driving force behind many scientific endeavors. While our primary interest may lie in finding intelligent, technologically advanced species, the discovery of any form of life would be monumental. Even microbial life on another planet would suggest that life is not unique to Earth and could be more common than we currently believe. In 1950, physicist Enrico Fermi famously posed the question, "Where is everyone?" a query that encapsulates the Fermi Paradox. Despite the apparent abundance of the necessary ingredients for life throughout the universe, we have yet to encounter any signs of extraterrestrial civilizations. This paradox remains a significant puzzle for scientists and has led to various hypotheses attempting to explain the apparent silence. One of the pioneering approaches to addressing this question was the Drake equation, formulated by Frank Drake in 1961. The Drake equation aimed to estimate the number of technologically advanced civilizations in our galaxy by multiplying several factors, including the rate of star formation, the fraction of stars with planets, the fraction of stars with planets, the fraction of planets where life, the fraction of planets where life actually arises, the fraction of life-bearing planets that develop intelligent life, the fraction of intelligent civilizations capable of interstellar communication, and the length of time these civilizations remain detectable. While the Drake equation was groundbreaking, it has become less effective over time due to several unspoken assumptions that do not align with modern understanding. For instance, the equation assumes that only one planet per star system could support life, that intelligent life will never spread to other worlds, and that interstellar communication would primarily involve radio signals. These assumptions have been challenged by new discoveries and advancements in our understanding of the universe. Today, we have a more refined approach to estimating the number of potentially habitable worlds and intelligent civilizations. We start with the number of stars in our galaxy, which is estimated to be between 200 and 400 billion. Surveys of exoplanets have shown that nearly all stars have planets, and many of these planets reside in their star's habitable zone. Among the various classes of stars, Sun-like stars, G-type, are considered prime candidates for hosting life, but other types, including K-type and M-type stars, may also harbor habitable planets. The fraction of stars with the right conditions for habitability is crucial. While more massive stars may burn out too quickly for intelligent life to develop, lower mass stars, particularly M-type red dwarfs, are abundant and long-lived but may pose challenges due to their stellar activity. Despite these challenges, the vast number of stars and planets suggests that there could be many habitable worlds. Advances in technology and our understanding of planetary systems have greatly enhanced our ability to detect and study exoplanets. Missions like Kepler and TESS, transiting exoplanet survey satellite, have identified thousands of exoplanets, some of which are Earth-like and located in their star's habitable zone. These discoveries have shifted the focus from mere speculation to a more empirical approach in the search for extraterrestrial life. The search for extraterrestrial intelligence, SETI, has traditionally focused on detecting radio signals from other civilizations. However, this method assumes that other intelligent beings use similar technology and that they are actively trying to communicate with us. Given the vast distances and potential technological differences, this approach may be too limited. Newer strategies include searching for technosignatures, such as the presence of large structures or unusual energy patterns that might indicate advanced civilizations. Despite these efforts, we have not yet found any definitive evidence of extraterrestrial life. This could be due to several reasons, including the vast distances between stars, the potential rarity of intelligent life, or the possibility that intelligent civilizations may not use detectable forms of communication. Another possibility is that intelligent civilizations may have short lifespans due to self-destruction or other catastrophic events. The future of our search for extraterrestrial life lies in enhancing our observational capabilities and expanding our understanding of life's potential diversity. This involves developing more powerful telescopes, both ground-based and space-based, to observe distant exoplanets and their atmospheres for signs of life. Instruments like the James Webb Space Telescope, JOST, and the upcoming Extremely Large Telescope, ELT, will provide unprecedented detail, potentially revealing the chemical signatures of life. Astrobiological research plays a crucial role in this quest. By studying extreme environments on Earth, where life thrives under harsh conditions, scientists gain insights into the potential for life on other planets. This research helps identify the types of biosignatures we might look for on exoplanets. Additionally, missions to explore the icy moons of our solar system, such as Europa and Enceladus, where subsurface oceans might harbor life, are essential steps in understanding the broader potential for life in the universe.